Hello everyone, today we're going to discuss an introduction to AVL software. This tutorial is particularly useful for the Aerodynamics and Performance course, but can be useful for any other interested individual who would like to run some aerodynamics analysis or aircraft or flying object design. So, my name is Dr. Afshin Rahimi and I'm a faculty at the University of Windsor, and I will be running over some basics concepts and introduction to the software in this tutorial. So AVL stands for Athena Vortex Lattice, and AVL is a program for the aerodynamic and flight dynamic analysis of rigid aircraft of arbitrary configuration. It employs an extended vortex lattice model. Remember that it is an extended version of the VLM or vortex lattice model for the lifting surfaces, together with a slender body model for fuselages and nacelles. This description is directly taken from the Mark Drela's web page for the AVL software that you can see on the screen. So this is the web page that this description is taken from, and I have underlined some of the important keywords in there. Not only you can run some aerodynamic analysis with the software, you can also do some dynamic analysis or stability analysis for your flying objects or aircraft designs. For that, the general nonlinear flight states can be specified in the program, and the flight dynamics analysis combines a full linearization of the aerodynamic model about the flight state together with specified mass properties. We will get to what are the files required for any of your simulations, depending on how in depth you want to be, but usually you need three types of files. One is the geometry of your aircraft, one is the run case for your aircraft, which basically simulates a scenario for which you want to simulate your aircraft or flying object in, and another one is a mass file, which includes the mass properties of your object or design, which basically helps with all the inertia and other parameters that relate to the mass of your object. So again, this definition is by Mark Drela, and this is taken from the Mark Drela's website, particularly the webpage for the AVL. Now, we're going to go through some of the basics today. We're going to discuss what is AVL useful for. So we discussed that from the quote that we got from Mark Drela. How does it work? Basically, the description again that we just discussed, but we will explain a little bit further on that once we go through some of the underlying aerodynamic principles. So we kind of discussed the first item. The second item is going to be related to when we discuss the underlying aerodynamic principles. And after we discuss that, we can get back to how now AVL does work using those underlying principles. So the content of this tutorial and the slides I'm showing are mainly taken from the Anderson's Fundamentals of Aerodynamics textbook, published by McGraw-Hill Education, and Mark Drela's. So the Mark Drela is actually the author of the Flight Vehicle Aerodynamics book or textbook, published by MIT Press, and he's the person who actually made the AVL software that goes with all these underlying fundamental principles or aerodynamic principles that are used and explained in his textbook, so that interested individuals can run aerodynamic analysis. Now, let's get into what vortex lattice method is, or in short, VLM. But before we get to that, we first need to review a simpler model, that is the lifting line theory. So recall that the lifting line theory is a model of a finite wing which allows the induced drag generated and the overall lift coefficient to be determined. So lifting line theory is a simpler model that we can use for a finite wing, this is important, that to be able to get the induced drag and the overall lift coefficient for an airfoil or a wing. For the simple case of an elliptical lift distribution, remember that elliptical lift distribution also is a very particular case of a lift distribution that technically only exists on a very particular shape of an airfoil that we will get to later on. We have lowest possible value of induced drag. So that means that this type of lift distribution on a particular shape of airfoil or wing is ideal for us because we have the minimal resistance from the airstream to it for a given lift coefficient and wing aspect ratio. So for any given wing aspect ratio and lift coefficient, the elliptical lift distribution would be ideal. And to achieve the elliptical lift distribution, we technically have to create an elliptical wing, which we will get to shortly why that is. But also we have to keep in mind that that's not always the case. So creating an elliptical wing is not necessarily the cheapest or the fastest or the most cost-efficient way of creating a wing, even though it's an ideal, and there are some alternatives to do that. Now, the lifting line theory, the simpler version of the theory that we just discussed, which is the lifting line theory, applies to large aspect ratio and unswept wings at the small angles of attack. So 3 conditions. 1, they have to be large aspect ratio. 2, they have to be unswept. And 3, they have to have small angles of attack. This theory was developed by Prandtl and Lanchester during the early 20th century. And it's useful for analytic results for simple wings. So if you have simple wings that fit this criteria, you can use the lifting line theory for those wings. This is basis of much of modern wing theory. For example, the helicopter rotor aerodynamic analysis, and this can be extended to the vortex lattice method that we will get to shortly. It is also the basis of much of the qualitative understanding of induced drag and aspect ratio. So again, even though the lifting line theory can be very restricted by these conditions because you don't always have all these 3 applicable to the design that you're working with, but it can be used for these analyses, or at least the preliminary analysis that you need to do for any of the designs that you're working with. Now, what does the lifting line theory does? Or what does it do? Basically, if you have this wing on the left-hand side, what the lifting line theory does, it replaces the wing, which is a finite wing, remember that it does have ends, with a series of horseshoe-shaped vortex filaments. So basically we change or replace the left-hand side, a wing, with the right-hand side, a horseshoe vortex. So the horseshoe vortex is going to show us what it is like for the wing to be modeled by a horseshoe vortex. And why do we use a horseshoe vortex? Because what we are trying to find from this modeling is basically the circulation that will result in calculation or determination of the forces acting on our wing, particularly the lift and drag, given the airstream that the wing is flying in with certain speed. So in the simplest form, we can replace the wing by only one horseshoe vortex. However, this will be very simplified version of the modeling, and therefore may not be necessarily capturing the best of what we are looking for. Additionally, what we get from this horseshoe vortex is the downwash distribution along the y-axis or the span of the wing for a single horseshoe vortex. Remember that the downwash is an effect of the wind blowing on the wing or airfoil, and the resulting forces creating a downwash due to the circulation acting on this airfoil or wing that we are now modeling with a horseshoe vortex. Now, if we try to improve the model we have for the horseshoe vortex, we need to add additional horseshoe vortices. So to do that, we need to create a distribution of vortices along the wingspan. So instead of one horseshoe vortex, we're going to have multiple horseshoe vortices and then superimpose the effect of all of them on the wing. So as you see, we have one that is going from span to span, then another one that is continuing a little bit inside the wing, and the third one, and we can increase these numbers as many as we want. But as you can see, the superposition of the effect of the various horseshoe vortices is actually what is going to give us a better estimate or a better determination of what the actual forces acting on our wing, including the lift and drag, are going to be. Given that we can get the circulation or the gammas from here, and then we can use those to calculate the lift and drag. But in here we do have a finite number of horseshoe vortices. Similar to what you would do if you were to calculate an integral for the area under a curve, you basically try to discretize it using finite number of rectangles and then calculating the area of those rectangles. Now the finer the rectangle spaces are, the more accurate your calculation or numerical calculation of that area under the curve is going to be when you're taking that integral. Similarly, the finer the number or the more number of these vortices we have, the closer this distribution will match the actual distribution of circulation over the wing that we have. So to improve the accuracy of our model, we need to increase the number of these horseshoe vortices, which takes us to this. So if we increase the number of those horseshoe vortices to an infinite number, and this infinite can be a large number, it doesn't have to be millions. Also, if you do have the computational power, you can do that as well. You will get a closer distribution to the realistic distribution of the circulation over the wing. And as you can see, it looks like an elliptical distribution. And this gives us a function of gamma equals a gamma y, which means gamma or circulation is going to be a function of the y-axis or the location on the span with the maximum value of gamma naught or gamma 0. Now the lifting line model allows solution for arbitrary lift distributions. But here we will consider a special case, that is the elliptical lift distribution. So for the elliptical lift distribution, we will have that function of gamma y equals gamma naught, the maximum value, multiplied by the square root of 1 minus 2y over b squared. So the y is the location on the span and b is the span. And with this, we can see that at the edges of the wing, so the two ends of negative half b and positive half b, or half of the span, or ends of the wing, we will have the circulation equal to 0. And that physically is correct because we don't have any lift in those two locations, so we're expecting them to be 0. Then for the downward velocity or the downwash, which we said is caused by the airstream acting on the airfoil, we will get W as a function of span location to be a constant value in this case, as maximum value of circulation gamma naught over 2b, which is the span, negative. And as you can see, it is not a function of the location on the span, it is a constant value. And this then gives us the induced angle of attack, which is shown by alpha I, alpha for angle of attack, I for induced, equals to gamma 0 or gamma naught over 2b the infinity, so the effect of the free stream velocity comes in, and that is equal to CL, that is the lift coefficient for our wing, over pi, which is a constant value, aspect ratio, which is related to the geometry of the wing we're working with. So alpha I will be equal to CL over pi aspect ratio. This is for the elliptical wing, which is the elliptical lift distribution, and that is the ideal case or a special case of a wing design with ideal characteristics. Now the induced drag for elliptical lift distribution can be seen to be clearly the drag due to lift. So CDI is going to be equal to CL squared, that is lift coefficient squared, over pi aspect ratio. The induced drag inversely is proportional to aspect ratio. And as we can see, if the aspect ratio goes to infinity because it's in the denominator, the full value of CDI or induced drag is going to go to 0, meaning that we won't have any induced drag for an infinite wing, because that's when you will have an infinite aspect ratio. Now for the elliptical chord distribution, if we want an elliptical wing having C, or the chord, as a function of location of the span, it will be required to be L prime, where L prime is the lift per unit of span, over Q infinity, which is half rho V squared, or dynamic pressure, multiplied by CL, which is the airfoil lift coefficient. Now since Q infinity and CL are constant values in this case, along the span, and L prime is elliptical, the lift distribution is elliptical, if we want the elliptical lift distribution, this equation says that we must have elliptical wing or elliptical chord distribution. That means for the ideal case of elliptical lift distribution, our wing has to be of elliptical shape, or the wing plan form has to be elliptical. So in general case, the lift distribution is going to have a new parameter that is E, or the Oswald efficiency factor. Now for an elliptical or ideal case of lift distribution, E is going to be 1, so CDI is going to be CL squared over pi aspect ratio. But in most cases, you do not have the ideal case. So what you expect is you expect the CDI to be more because it's not ideal anymore. And that means you will have the E, or the efficiency factor, less than 1. So because it's in the denominator, the CDI value is going to grow when you do not have the elliptical lift distribution or the ideal wing plan form. Now to read more about this, you can see section 5.3 of the Anderson's book that we discussed at the beginning of this slides. But let's get into the limitations of the lifting line theory. So the lifting line theory works well for moderate to high aspect ratio straight wings and unswept wings. Plus, we earlier said that it only works for low angles of attack or small angle of attack. So if we do have other scenarios that don't fit into these criteria, we need an alternative approach. The alternative approach will be useful for low aspect ratio wings, similar to this picture, or this wing platform. Swept wings, similar to this wing platform. And delta wings, similar to this wing platform. So in any case of these three, we won't be able to use the lifting line theory to get an accurate estimate of the actual lift and drag forces or lift distribution for the wing that we are working with. So what is the alternative that we can use? That takes us to the vortex lattice method. So the vortex lattice method is what we discussed is being used in the AVL software that Mark Drela has developed, and we will be using or going through these tutorials, that gives us a more accurate estimation of lift distribution and its resulting other parameters for the wing or the geometry that we're designing, and can be applicable to a wider range of designs that the lifting line theory cannot cover. So the VLM is an approach which can be used for any wing platform. How it works, it places discrete horseshoe vortices in a grid or lattice of panels over wing surface. So if you recall, in the lifting line theory, we were able to only put the horseshoe vortices along the span, but we couldn't really place them along the chord. What the vortex lattice method is going to do, it's going to add a new dimension to our ability to place the horseshoe vortices on the wing. That is, it is going to allow us to now put the horseshoe vortices also along the chord in addition to along the span. Now, how does this help? It will help including multiple lifting lines distributed along the wing chord. So in addition to the span, we can also add the horseshoe vortices along the chord. Each vortex will have an unknown strength, the gamma that we are going to need to find the value of, and we also needed to find the value of in the lifting line theory. And how are we going to find the values of these? We need to solve a series of equations or a system of equations numerically by applying the boundary conditions that include the kata condition and the flow tangency condition. Using these boundary conditions and having our system of equations created by the number of panels that we put on our wing or lifting surface, we would be able to solve the system, and that will give us the strength or the gamma for each of those panels. And the collection of those strengths and the superimpose or the superposition of those strengths will then give us the lift distribution all over the lifting surface that we are working with. So to visually look at this, if you remember for the lifting line theory, we were able to put only the horseshoe vortices along this span, meaning we would only have 1, 2, 3, 4, up to 8 horseshoe vortices that we could place along the span. What the VLM or the vortex lattice method allows us to do is, in addition to the span-wise distribution of those horseshoe vortices, we can also add chord-wise distribution of these horseshoe vortices. So now we will have panels on our lifting surface or wing, which is now shown by this green panel. So this green panel is one of the panels on this surface. So we have 4 chord-wise, 8 span-wise. 4 times 8 is 32. So we will have 32 panels in this distribution. Now, to get better estimates, you can work with the distribution of these. So you can increase the number of chord-wise and the span-wise panels, and that will, the finer or the grid is, or the more panels you have, you expect to get a better estimate or more accurate estimate. But that is from the numerical point of view. Now on each panel, as you can see, we have the same replication that we saw for the lifting line theory, that we were replacing the wing, in this case the panel, by a horseshoe vortex, and then this vortex had an unknown strength gamma. So the point or the objective of this distribution is to put gamma on each of these panels. They are going to be unknown, using the boundary conditions for the wing that we have, and numerically solving a system of equations to find the unknown gamma or strength values for each of these panels. And once we have those, we will be able to find the overall distribution for lift and drag for the lifting surface or the wing that we are working with. So basically, what the AVL software does is, when we give it a geometry like this wing, and then providing information on how we want our grid system or the number of panels to be, it will create that system of equation for us. It will also apply the boundary conditions that we discussed, and what it will give us is the distribution that we are looking for. So that's the lift, drag, and other parameters that we are looking for when we are analyzing the wing or any lifting surface, and that will be important to us in that analysis. So to read more about the VLM method, you can read section 6.5 of the Drela's book that explains more detail and mathematical explanations and proofs for this method of VLM and how it can be used. And as we said, this is authored by the creator or the developer of the AVL software, Mark Drela, and that basically has a very good agreement between the textbook and the software. Now we get to AVL. So this diagram is actually a wing and a tail created in AVL software. And as you can see, we have these grids or panels that are visually shown for this particular geometry. So what this software will do, it will create that system of equation for us, calculate all the unknown strength, and then gives us the distributions and other characteristics that, from the aerodynamic standpoint, we are looking for us to be able to analyze that design and figure out whether it's a good design or we need to further improve it. So the Athena Vortex Lattice is a free open source vortex lattice code by Mark Drela that can be used to analyze wings and entire aircraft configurations. And this particular geometry is actually a sample geometry that is provided by Mark Drela, and the name of this is called Vanilla. So this is the Vanilla aircraft that is created and available as a sample file with the packages that we get for the AVL software, that we will get to next time when we go to discuss the basics of the software and what are the things that we need to use for the software. So next time we're going to go through program structure. So we were going to discuss where you can download the software depending on what system you're working on or operating system. How can you run it and open it? And what are the required files that you need to be able to work with the software and work on the design that you have in mind.